This lesson entails a comparison of polyolefin fiber reinforced self-compacting concrete with a conventional polyolefin fiber reinforced concrete. As it has been previously explained, recent trends for fiber reinforced concrete are in the context of high-performance concrete, and among those, the combination with self-compacting concrete is currently the one that has shown more advantages. Concisely, with steel fiber reinforced concrete, research has shown that remarkable improvements can be noticed in the fracture behavior. This increase in the residual strengths takes place due to improvements of fiber positioning as a consequence of the flux of self-compacting concrete. Such effect has been recently studied in our research group with polyolefin fiber reinforced concrete, as can be seen in this course. However, vibrated conventional concrete is still the most commonly used type of concrete and may provide some other advantages. In any event, a comparison between self-compacting polyolefin fiber reinforced concrete and vibrated conventional polyolefin fiber reinforced concrete was needed in order to support some of the conclusions of other campaigns. The main difference relies on the pouring and compaction of the mold. While in the vibrated conventional concrete, a standard pouring method requires pouring the mold from the center, using self-compacting concrete, the pouring position recommended in order to avoid overestimations is from the side. Compaction is reached by vibration in vibrated conventional concrete, while in self-compacting concrete the action of its sound weight permits filling and leveling the mold without any external energy. The mix proportioning has to be modified maintaining the water to cement ratio and the cement dosage. The design of the mix was performed in order to compare the two types of polyolefin fiber reinforced concrete. Therefore, it was sought to produce two plain concretes with similar fracture energies, decisive in fiber reinforced concrete. As can be seen in this slide, the fracture properties were very close to each other. Regarding the other mechanical properties, it seems that tensile strength and compressive strength of the combinations of vibrated conventional concrete and self-compacting concrete studied were slightly influenced by the presence of fibers, and in another note, the modulus of elasticity might decrease with significant amounts of fibers due to the worse compaction of the fresh concrete. In any case, all the results remain within the margins of a standard experimental scatter and should be handled carefully. Let's look now at the fracture behavior of polyolefin fibers reinforced concrete. I'd like to start saying that the appearance of standards and codes at the beginning of this century has boosted the use of fiber reinforced concrete and has supplied tools for the structural design. It is worth noting that they have clarified some structural requirements that were based on the experience with steel fiber reinforced concrete. Comparing vibrated conventional concrete with self-compacting concrete with moderate fiber contents, it is difficult to identify improvements due to the use of self-compacting concrete. Yet, some improvements can be seen due to a better orientation factor, just as noted in the case of steel fiber reinforced concrete. The residual strengths of both types of concrete reinforced with 10 kg meter cube met the requirements of the standards. While self-compacting concrete had higher values of strength, same proportional results were found with vibrated conventional concrete. This was due to the higher value of the strength at the limit of proportionality using self-compacting concrete. Note also that the requirements of the European standard were fulfilled too, with FR1 clearly exceeding 1.5 megapascals. Summarizing, as expected, vibrated conventional concrete reinforced with 10 kg of polyolefin fibers and self-compacting concrete reinforced with 10 kg of polyolefin fibers can meet the requirements established in the standards that permit the consideration of the contribution of the fibers in the structural design when a polyolefin fiber reinforced concrete element is desired. The effect of the flux increased the residual strength of the structural polyolefin fiber reinforced self-compacting concrete, and the difference in the fracture behavior needed to be studied by analyzing the fracture surfaces. The effect of the walls of the mold seemed to have a significant influence on the positioning of the fibers using vibrated conventional concrete specimens, and in the specimens manufactured with self-compacting concrete showed a more homogeneous fiber distribution in spite of the absence of a standardized filling procedure of the molds. Thank you for your attention.